Hi, everyone, and thanks for joining me today. My name is Will Cunningham, and I'm the head of high-performance computing at Agnostiq. And today I'll be talking to you about Covalent, an open source workflow orchestration tool for heterogeneous and distributed computing. So from our angle, we really see quantum computing as driving the need for a greater degree of heterogeneity. Of course, quantum workflows these days in a simple machine learning experiment use combinations of CPUs, GPUs, as well as quantum processors. More broadly, we see images like the one here representing how people are interacting with high-performance computing resources. Often it's the case that people are working with multiple clouds, multiple supercomputing clusters. They have data that's passing between their local workstation and cloud resources. And it can be very difficult to manage all of this together. And this introduces a great degree of operational complexity on the part of the user in order to actually effectively utilize these resources. When we think about how complex this can really get for new teams entering the space, we can think of it in these terms. Users need to decide all of these things. How does a task run? Where does a task run? How is their task going to be packaged? How is their data going to be shared? How are users going to be authenticated? And oftentimes it's the case that the short-term answers to these questions are not going to be the same as the long-term answers. What we're attempting to do with Covalent is to close the gap between the different degrees of complexity when it comes to interacting with HPC. Here on the left, we see there are three axes of complexity: domain knowledge, hardware knowledge, and software knowledge. What we want to do is compress this into just one dimension of complexity so that the domain experts, the machine learning researchers, the quantum computing researchers, computational scientists more generally, are able to leverage these resources without needing to know too much about operational practices or how the backend hardware actually works. So Covalent is a workflow orchestration platform for heterogeneous computing. It acts as a single entry point to the broader landscape of compute with a nice visual user interface so that users can easily understand where their data is going, where their money is going, and track their workflows in real time as they're executing on a variety of remote backends. We have integrations to lots of different resources at this time, everything from classical public clouds on Google, AWS, and Azure, as well as quantum clouds, HPC clusters through Slurm executors, and of course, everything can run locally on a Dask cluster as well. I'll describe a little bit more of that later. Covalent also supports workflows which use heterogeneous hardware, but also heterogeneous software. What this means is that because we see the need coming from legacy HPC integrating with more modern tools, this implies that you're going to have older code written in perhaps C++ or Fortran mingling with newer code in Python, as we see is popular in AI and machine learning, data science, and quantum computing. There are just three concepts that you need to understand in order to get started with a tool like Covalent. The first concept is that of the electron. The electron is a granular task in a workflow, and it's constructed by simply putting a ct.electron decorator on top of an existing Python function. By doing so, it means that we transform this ordinary Python function into a class object, which can contain all sorts of metadata about how invocations of that function actually ran, from benchmarking information to package dependencies to file dependencies, you name it. The second concept is that of the lattice. The lattice is a workflow definition, also a Python function, and it's constructed by, again, just adding one decorator, this time ct.lattice, on top of an existing Python function. This function, as you can see on the left-hand side here, is simply going to pipe data around between different tasks as they execute. So what this means is that even though it's a regular Python function, when each of these tasks is going to be operating, executing in variety of remote backends geographically distributed, it's going to build your data pipelines under the hood, move the data around, make sure that packages are installed so that the end user doesn't have to do this on their own. The third concept is that of the dispatch. A dispatch is simply an asynchronous deployment of your workflow to the Covalent server. So what this means, if you're familiar with something like other job scheduling tools, Kubernetes, Slurm, Batch on the cloud, for instance, This is going to act at a layer above those other tools so that you can manage workflows across these platforms and not be locked into any one single platform. We find that it's really important when we're designing this kind of tool to enforce that there are really minimal code changes required on the part of the end user. So what this means is that if you're trying to take an existing code base and make it compatible with Covalent, all that we ask is that you add a single one-line decorator on top of existing functions to transform them either into electrons or lattices. And this will allow you to send them then to the Covalent dispatcher, and by way of the dispatcher, you'll be able to execute your functions on remote machines. Now you'll notice on the right-hand side here, I have 3 examples. I'm using AWS Braket, which connects to their hybrid job service. I'm using a Slurm executor, and I'm also using a Qiskit runtime executor. So this is really geared for a quantum and HPC type example. And you'll also notice that I'm specifying very little information here. I'm specifying just really resource requirements, and in some cases, such as the first one, the particular device that I want to execute on. But I'm not specifying operational information, for instance, how to authenticate, how to, which particular queues I'm connecting to. And this is because all of this information can be stored in a configuration file after the resources are set up. So there are a variety of ways to interact with Covalent. But in this particular example, once it's set up, it becomes very easy to swap these decorators around between different functions to tune your resources, tune how much it costs to run the workflow, so that it's very easy to have visibility into what are the actual resource and cost requirements of your workflows. Covalent uses a client-server architecture. So this means that there's a Pythonic SDK, which is going to be downloaded onto the user's local machine. There's a Covalent server as well, which can live on the user's workstation, or it can be deployed into the cloud. We have a variety of different deployment methods, everything from Docker to Conda and pip. Covalent can run as a systemd service. There are machine images on the cloud that are available for it. Really, there's a lot of flexibility in how it can be deployed. Now, the Covalent server includes a few different components that I want to touch on here. It includes a dispatch service as well as a user interface. The dispatch service is going to be responsible for orchestrating all of the different tasks and relaying them to different remote backends. The user interface, of course, is going to be what the user interacts with in order to inspect their workflows. An example you can see on the right here. Covalent also has a long list of executor plugins. These plugins allow the end user to customize their version of Covalent Server so that they can keep the entire thing lean while interacting with exactly the resources that they need to interact with. So this could be anything from Kubernetes to HPC resources like PBS or Slurm, different cloud resources, even quantum resources like Braket, hybrid jobs, and Qiskit runtime. And I'd also like to highlight here that we provide a nice template in a repository for custom executors. So if we haven't provided an interface that end users are interested in hooking up Covalent to, we provide a very clear section, a run method, where users can define the API interface between Covalent Server and their particular backend. It's about 50 to 100 lines of code, and it's very easy to do. Now, on the right-hand side here, I'll come back to this in an example, but I want to highlight a few different components that you're looking at. In the center, you see a visual representation of a particular code. So the tasks here are going to be represented by the different bubbles. There are green check marks, which you might be able to see, which are going to represent the status of each task in the workflow. And so by monitoring it in this user interface, you're able to really watch in real time as tasks execute, as they succeed, as they fail, inspect error messages, trace back issues across different platforms without having to log into different systems and retrieve logs on your own. On the left-hand side, we display all of the different workflow level metadata. So this means that you can see everything from benchmarking information to interactive inputs and outputs to the source code itself. This is particularly useful in the case that you're running lots of experiments. Not everything gets checked into version control, and you really sometimes are interested in what were the exact parameters you used, what was the exact version of the code that you used for a particular invocation of your workflow. On the right-hand side, we see all of the task level metadata. So if you click on one of these nodes in the graph in the middle, then you'll be able to inspect metadata for that particular task. We include here the status, benchmarking information, interactive inputs and outputs, executor information, as well as the source code once again. The advantage of having this interactive information, as I'll show in a notebook in a moment, is that you can copy these. So if you click on them, it'll copy to your clipboard. You can take them back to your Jupyter notebook and start interacting with them immediately. So for instance, if you have a particular task where an output is a trained machine learning model, you would be able to take that directly back to your Jupyter notebook, recompile it, interact with it, retrain it, use it for inference, and it becomes very easy to interact with partially checkpointed results, as well as the final result of the workflow. Covalent also includes some project management features so that you can organize your dispatches by projects and experiments. This is particularly useful in the case that you don't necessarily know beforehand which data is going to be useful. So here we allow tagging and other sorts of organizational features so that it's manageable when you have thousands or tens of thousands of dispatches. Covalent supports a growing ecosystem of both hardware as well as software. I've touched a little bit upon the classical and quantum resources here. Again, this is a growing list based on how different customers and end users are requesting features. We also support any and all software packages that are used in data science, machine learning, and quantum computing. And this is because Covalent is operating a layer above these other packages. So just as you'd be able to import these packages in a regular Python function, you can import them inside a Covalent task or Electron as well. Now, this last point here, I just want to touch again on the heterogeneous languages. So while the orchestration is done in Python, your individual tasks can be written in other languages. And in order to support this, we leverage bindings between Python and different languages. So for instance, you see Python here, and this would be, for instance, if you want to invoke a different Python module, or perhaps invoke a function that's written in a different version of Python. For C++ and Bash, we're simply using a combination of subprocesses and bindings in order to translate inputs and outputs between Python and other languages. We do plan on supporting further languages in the future, such as Julia, Fortran, etc. At this point, I'm going to switch over to some notebooks to demonstrate some of the features of what it's like to actually use Covalent. So I'll mention just briefly, this is our documentation page on covalent.readthedocs.io. We've made a lot of changes to it recently, so if you haven't checked it out in the past few months, take a look at it. A lot of what I'll be going over in the next couple notebooks can be found here as well. So this example here is our quick start guide. The quick start is designed to give a really crisp idea of what it's like to actually install and get started and run your first workflow with Covalent. There are just 3 steps, really, to get it installed and running. The first step is to create a virtual environment. We recommend this so that Covalent is properly isolated from the rest of the operating system, and there are no conflicts between your operating system's version of Python and any dependencies that Covalent may pull in. The second installation step is going to be to run pip install Covalent here, just as you would with any other Python package. And then the third step is going to be to run Covalent start on the command line. This is going to start the Covalent server. Natively, it's going to also start a Dask cluster on your local workstation. And the reason for this is because as you're running different workflows, you want to ensure that your resources are not going to be overloaded on your local system. So for instance, if you're recording a video or if you're giving a presentation and you start running lots and lots of workflows, you can be sure that your computer will not crash and you will be able to continue with your video presentation. So in this very simple hello world style example here, I'm showing some very basic code. I'm just going to be constructing a few different tasks. And again, notice that I've added this ct.electron decorator on top of each of these 3 functions. Now, I've explicitly marked it as local execution just to emphasize, again, everything is going to be running locally on my workstation here, although this is not needed in practice. Now, Down here, I'm defining the workflow function. So this is, again, just a regular Python function. It's going to call all of these three different tasks up here, pipe some data around, do some math, use some loops, etc. And then finally, I'm going to call ct.dispatch to asynchronously deploy my workflow to the Covalent server. So because I request the result immediately and it's asynchronous, it's simply going to tell me that it's running. But at this point, I could go into the Covalent user interface and monitor progress of the task. And at the same time, I could close my Jupyter notebook, kill the kernel, not worry about it dying for a particularly long-running task, for instance, where things may be in queue or computation may be quite long. So if I go over to the Covalent UI, I can copy this dispatch ID that I've gotten here. I can go over to my user interface. This is the dashboard where you can see the list of all of the dispatches. I'm going to search for this dispatch, click on it here, and now you can see I have a visual representation of the code that I just displayed. So you can see, again, everything is running locally. You can click on tasks and start to view inputs and outputs. And really, you can start to get some insight into all of the different intermediate data that's checkpointed in this workflow. So for instance, for this multiply function, I can very transparently see the arguments and the keyword arguments for that particular task, as well as the result. And if I click this, it's going to, again, copy it to my clipboard so that I can bring it back to the Jupyter notebook and interact with it there. Now, this is a fairly straightforward example. So I'd like to show some more interesting features of things that you can do with Covalent. So this next example is going to be doing a multi-cloud quantum circuit simulation. Now, the experiment itself here is not super groundbreaking. We're just going to be taking some randomly generated quantum circuits and evaluating them on different backend devices. But the point is, it's high compute. It requires, in many cases, executing this many times in parallel. And so it becomes important to be able to dispatch this in a way that you don't have one task waiting for the next task if they're not logically blocked. So I'm going to be using a fairly straightforward stack here. I'll be using PennyLane as well as Qiskit in order to construct and evaluate my circuits. So the first task here that I want to look at, I'm going to be generating a random circuit, okay? And I'm going to be doing this just locally. I can specify the number of qubits and the depth, and this is going to return to me a random circuit. Now, for the next 4 tasks, I'm going to evaluate this in 4 different ways. I've summarized it up here. So one of them is going to run on Azure Batch. Another one will run on Google Batch, on Google Cloud. Another one is going to run on AWS hybrid jobs. And finally, the last one is going to be using an IBM state vector simulator running on the local Dask cluster on my workstation. So the idea here is to give you some insight into what pieces of information does the end user actually have to interact with or understand in order to dispatch tasks to these different backends. So as an example here, we have the Azure Batch executor. Now, we've sort of taken a middle ground approach to terminology and vocabulary here, because anybody who's familiar with Azure Batch is going to know some of this information. They're going to know their tenant ID, for instance. They're going to know their batch account URL or the name of their pool. But then we standardize other pieces of information. So for instance, the number of vCPUs, the amount of memory, and the time limit is going to be available across all of these different executors. So if I scroll down a little bit and compare to what the Google Batch executor looks like, then you can see, again, I have some cloud-specific information, and then I have this standardized piece of block of information here. Now, the reason I'm showing this is because most often resources will be set up by a system administrator or a cloud engineer on the team. And once that is done, these resources essentially will be static. So what this means is that all of this information up here is static. It's going to live in a configuration file, and it can be omitted when actually constructing and working with these executor objects. So ultimately, the end user really is just going to be specifying number of vCPUs, amount of memory, and the time limit for their particular jobs. So that's really the experience that we're going for, is that the domain experts are thinking about resource requirements, but not operations and not infrastructure. So if we scroll down, I'm going to show a couple more examples of this. So we have bracket hybrid jobs here. In this case, it's a hybrid quantum job service. So the entire classical quantum task is going to be containerized, sent off to Amazon Bracket, and it will be evaluated on their system. So we can specify, for instance, both the quantum device. Here we're using the SV1 quantum simulator. Although if you wanted to run on real quantum hardware, this would be the piece of information that you would swap out in order to evaluate that circuit on a real device. We also specify a classical device here. This is an instance type, M5.large, and this is simply going to correlate to some number of CPU cores, some amount of memory, and some networking speed. So if we continue scrolling down, you can see that, again, inside all of these functions, we're essentially using PennyLane and Qiskit to evaluate these circuits. Continuing down, ultimately, we're going to combine these results and we're going to produce a plot right here. So this is the last task in my workflow. I'm going to produce a plot which compares the results of the circuit evaluation on all 4 of these different devices. Right here, I have my workflow definition. You can see an example of it. So I'm just iterating over the different functions here in order to evaluate these circuits in parallel. Now, I want to note here that I'm actually going to be running this not locally, but instead on a remote Covalent server that I've deployed in AWS. I've done this using machine image. We also have methods, if you're interested, to deploy it with Terraform or Ansible. We try to provide lots of different ways to make it easy to deploy this. So we have right here, I'm specifying the address as well as the port. And now this time, once I dispatch this workflow, it's going to send it to the server at this address instead of localhost. So I can now navigate to my cloud-based UI, and I'm going to see this piece of information instead. So I see this workflow. It's going to have, again, a visual representation of all of my different tasks and of the workflow in its entirety. So if I zoom in here, you can actually see where each of these tasks executed. So we have the random circuit generation, which generated the input data, is running on the Dask cluster locally. One task is running in Bracket, one is running in Azure Batch, one is running in Google Batch, and this last one is running in Dask. Now the output here of all of this is going to be a plotly plot. So again, if you copy this and you copy it to your clipboard here, just by clicking on it, and then you go back to the notebook, you can actually copy it into a cell. And this is what would copy off of your clipboard, is this serialized piece of information that can be unpacked using Pickle. And so when I load this, so essentially I do Control V and then execute the cell, and I get this plot out. Now, this is really nice because I don't have to worry about file formats, storage, what data was in it. I can just click and paste and see my plot immediately. So it becomes very easy to, again, not just work with Pythonic or mathematical objects like models in the context of machine learning, but it's also really nice for visualization and data science applications where users really need to be able to share this type of information with other users without necessarily worrying about what packages they have installed or how they can reproduce it, because it's really designed in its entirety to be as reproducible as possible. So with that, I will conclude my talk. I'll just say Covalent is the simplest way to orchestrate and scale workloads across heterogeneous computing environments. It's open source, so if you like what we're doing, visit us on our GitHub page, give us a star, contribute, open issues, join our Slack channel, join our newsletter, engage in any possible way that is comfortable for you. And I look forward to conversations about use cases and feature requests. Thank you.
Thank you so much, Will. Now, probably it's a good time to check if Will can. Oh, awesome. Hey, how you doing?
Hi, everyone. How are you doing?
Thank you so much for joining us. What time is there now?
about 6:30 in the morning.
Thank you so much for doing this effort. Okay, questions from the audience?
Sorry. Hi. Yeah. Sorry, you are supporting only Slurm as executor. You plan to support more executors like SandGrid Engine or LSF or something like that. And if not, it's really difficult to adapt the software to this kind of schedulers.
Yeah, that's a great question. So at the moment, we find most of our users are interacting with Slurm-based systems, and so that's where we've put the most effort in. That's you know, in the case of HPC, that's the only one that we've released publicly so far. We have a few you know, internal plugins as well for instance, LSF and PBS. I think if you're familiar with interacting with multiple job schedulers, you'll know it's mostly an exercise in translation, and so you know, we do anticipate that as more users are requesting the deployment of these plugins, then we will start releasing them. So the answer is yes, it's very easy to support and extend. And at this point, we're waiting for requests.